But I'll start with a problem. You know, the trouble is when you build a chip, it's a real multi-dimensional problem. You've got to figure out the specs, you got in the applications, you've got to kind of decide on a process node or maybe nodes, then even a variant in between the nodes. You got to get a metal stack. In some of the more advanced processes, there are a lot of VTs that you need to pick from, and they offer performance at some extra cost. You still got to manage performance and power, and then you got to integrate everything. So it's really difficult for, for you guys. Most of you guys build chips. And our job here is to make that easier. Solve the Rubik's Cube. And that's really what we're about at True Circuits as much as anything else. We use a lot of our innovation a lot of our innovation is to build tools and things that allow us to have our entire portfolio at all the different process nodes, which is maybe up to 60 right now. It allows us we build a highly programmable, for instance, PLL, so it could be used multiple places across the chip with, one license fee, and you can program it to do whatever it is that you need to be done. We automatically prepare the IP for any metal stack or any oxide thickness. So, this is a problem. Many times you get all your IP lined up, somebody in the management chain decides to use a little bit different process node or another metal stack, and like a trap door, several of your IPs fall out. We also provide a lot of timing support, so we understand a lot about the application, and we can help guide you through the process so you don't have to become an expert in jitter or different reference requirements that might exist for the different interfaces, serial interfaces. So we have hundreds of part numbers available. If you went to our website right now, you'd be filled and you'd scroll and scroll and scroll, just so that all the different process nodes, all the variants, and all the different speed grades are all available. So, and then the last, we try to make integration easy. So we typically provide all our IP as a single hard macro. We'll have decoupling, we'll have guard rings, we'll have keep out. You typically only have to hook up to a core power and a couple of timing domains. And really also we try to keep the commercial side easy too. So the real thing, we want to do is provide something with support and make it as easy on you as possible. You already got a hard job to do just procuring the maybe up to 75 IPs that you might need for a typical chip these days or more. So True Circuits has been around a long time. We're one of the leaders, I would say, in the analog IP space. Let's go back. We were founded in '98. We're all of our R&D and whole companies in Los Altos, near Palo Alto. We're leaders in analog design. But not only analog design, like I talked about, we use a tremendous amount of automation in designing, in characterizing, and even testing our IP. So if you looked at our IP, we look a little more like soft IP than hard IP. You'd see something that looks like a computer language that encodes the placement as well as the circuit design and even the simulation and testing. We have a highly automated test environment. So when we go to another node, we take our entire portfolio, put it on one test vehicle, run that, 5-way split, minus 40 to 125, and then all that data is collected automatically. We create a report automatically. And then our goal is not just to meet spec, but to close the loop that SPICE predicted it should work like this, and it does work like that. So that allows us to have a fairly diverse, portfolio. Back again, this has happened. I think that there's an automatic feature in here. So we have some very high clock multipliers. We have a new PLL that has multiplication up to 250,000. We have PLLs that do certain specific things like deskew, You might put that in some kind of a PHY or some kind of a local circuit. We have what we call a general purpose PLL, which is smaller, lower in power, and actually less expensive to license. And then we have two new PLLs, an ultra PLL that I'll talk about a little bit more, which has very high multiplication and very low jitter. And then we did an IoT PLL, which is much lower in power, that can run off 32 kilohertz. So you can not only run at lower power, but by being able to multiply, in increments of 32 kilohertz, you can manage your power. You could even turn off the PLL and still have the 32 kilohertz reference clock heartbeat. So, in IoT power, many times it's all about power management. So this PLL offers some more interesting architectural options. We have a delay lock loop, which is used in DDR interfaces, Amplify. It's kind of a specialized element in a timing architecture that you might create. We have a DDR PHY, which we've announced that will tape out a little bit later this year. I'll talk a little bit more about it, but the DDR is a really fairly sophisticated product. It's meant to be able to handle a lot of physical variability. It's able to build PHYs that might go across 2 or even 3 sides of the chip and still be able to close timing. It has a lot of automated training. Every pin automatically adjusts. So DDR is a parallel interface. So having every pin constantly be able to be trained makes it easier to build a board, easier to build the chip, easier to build the package, and then, like we talked about, a lot of emphasis on closing timing and a lot of automated training. We have, like I said, just about every process variant of TSMC and Global Foundries and UMC that you'd find, even back to the older processes. So because we do things in an automated way, we can actually produce a modern architecture in an older node. And that could be interesting because there's a lot of energy in some of the older nodes because of the IoT world, where you don't need something that is that sophisticated. In fact, you might even want to take advantage of better analog properties in older processes, or you might have some kind of sensor technology that marries itself nicely to an older node. So, in general, we build things that are high performance or general purpose. We have some products that are very low jitter, and also the architecture we use is very process intolerant, roughly, of process. So besides meeting spec, it tends to be robust. If you get outside of the the design envelope, lower voltage, higher temperature, it tends to have a small degrade in performance but not fall off a cliff. And that's especially important in some of the harsher environments, or where you expect in the real world of the customer they might, have a voltage which is outside of the spec. As I talked about, we have some very large multiplication, so you can build up, say, a gigahertz clock from a 32 kilohertz crystal, which could be interesting. Small sizes and form factors, and then a lot of pin programmability. So typically in the world of analog, you've tended to build things that are specialized for every condition, but here we use pin programmability to change bandwidths and to adjust for certain frequency ranges. So that allows you to use it in a more powerful way. Let's see. Talked a little bit about the IO PLL. We probably covered it pretty well. Again, meant to be very low power. It runs off core voltage, so it's easy and lower power. It'll still multiply up to 8,000. So again, you could take a 32 kilohertz crystal and build a 250 meg clock, which is probably what you might want for a lower end ARM processor that might be the kind of thing you would use in an IoT or a wearable. The Ultra PLL is like I said, this is a product we announced last year. And it's a brand new architecture for us. It's a pretty state-of-the-art digital architecture with an LC oscillator. So it takes sort of a traditional LC PLL that would work in a narrow range. Now it works in a larger range, and it takes some of the limitations that you had and gets rid of those by use of the digital architecture. Very low jitter, less than half of a picosecond. So that's the kind of thing you might need for a very demanding reference clock spec for a high-speed SerDes. Also has fractional bits, up to 26 fractional bits, so you can build a very precise frequency from any reference clock that you have. And then that also allows spread spectrum support, where you're varying the frequency to spread the electromagnetic energy over a wider bandwidth. So I know it's going to do that. This just talks a little bit about the applications. So again, one of the things we try to do is when we talk to customers, they bring us specs, and we say, that's great that you have specs, but let's make sure we talk about your problem. What is the problem, the timing problem you try to solve? And since we're experts in timing, we try to help solve the problem rather than just meet the spec. And so we try to, categorize whether you're doing sort of core clocking, maybe you want to do D-skew, maybe you have an ONTHE interface, something like that. We try to understand the specs and guide you guys through it. Again, everything's sort of meant to make it easier, This is an area you don't have to be an expert in, won't be too hard to integrate. We'll keep the commercial part simple. So that's about it. Any questions or comments?